Of course, the motion in itself is more complicated than just the motion of the center of mass, right? It rotates. We have to account for that later. But for the moment, we're just looking for a center of mass. As you can see, it's really important in describing at least partly the motion of the rigid body. So last time we did, oh, I don't have it here anymore. What did we do? Oh yeah, hemisphere and then a hemispherical shell. And triangles, rectangles, things like that. Let's look at the cone now, a solid cone. We don't know where the center of mass is, but if we divide it into disks, then we know where the center of mass of each disk is. All right, if I have disks like this, tiny disks of width delta x, I can easily find the center of mass of each disk. Well, I know the center of mass is going to be on that horizontal axis x. That's the axis of revolution of symmetry for the cone. And then for each disk is going to be at the center of each disk. And then I need to add them all up, weigh them by their mass, and then find the center of mass that way. So we just saw the same procedure as yesterday. First we look at the volume of each disk. Oh, here I see I've introduced an angle alpha. So if I call x the position of the center of mass of the disk and r the radius of the disk, I see that tangent alpha r over x. And then if I go further for the full length of the cone, that's h, there the radius of the cone is a, so tangent alpha is also a over h. So that gives me access to r, ax over h. I want r because I'm going to need it for the volume. So volume of a disk is just the area of the disk times its width. So the area, it's pi r squared, and the width is delta x, and r squared is just going to be pi a squared x squared over x squared delta x. So that's okay. Mass density, remember we assume that all the objects have uniform mass density. So rho, that's the mass density of the whole cone and also the mass density of each ring. For the whole cone, I have m over v, and v, that's the volume of a cone. I can't remember it, but it's on page 10. 1/3 of pi r squared, so the radius of the cone is a, times the height, this is h. I multiplied Tappenborn by 3 just to tidy up a bit. And that's also the mass density of each ring, each disk, sorry. So that's delta m over delta v. So I have rho, I have delta v, so I can find the mass of a disk. It's going to be delta m equals rho delta v. Rho, I have it just above, and delta v, I have it above, pi a squared x squared over h squared delta x. So pi a squared, that cancels out. I'm left with 3. Okay, I'm going to write on the next slide. So delta M equals 3m over h squared, no, h cubed, because there's h squared times h, or h times squared. And then I have delta x squared delta x. So now I have all the elements to find the position of the center of mass. I know that by definition it's going to be the weighted average XCM of all the centers of mass of the disks. So it's going to be delta M times the position X of each center of mass, 1 over M disks of 3m over h cubed. Delta M is x squared. I multiply by, okay, just write it then. X squared delta x times x. So the m's cancel out. And then you know the drill now. Yeah, I can just write like this. 3x cubed delta x. And then I'm going to say that this is the area of a small bar underneath the y equals 3x cubed curve. And then if I take the width of the small bars to go to 0, I'm going to turn, well, if I add the area of all those small bars, I have an approximation to the area under the curve. And then if I take the limit delta x to 0, I'm going to have exactly the integral, exactly the area under the curve, which is the integral. Right? I want to say take delta x to 0, and then xcm is going to be the integral. So x is between 0 and a. No, sorry, and h, that's the height of the cone. So I integrate from 0 to h, or 3x cubed dx. And now I know how to integrate this. 3, that's just a constant. Then the integral of x cubed is going to be x4 over 4. Yeah?
So where did the h cubed go?
Oh yeah, forgot about that. There you go. So that's no good, right? Because I should find a distance, and that's the distance to power 4. So that's not good. So I have got to divide by 1 over h cubed. So then I'll have a distance, so I'll be okay. See how dimensional analysis is handy to pick up mistakes. So I'd forgotten it here and here. So I have 3 over h cubed, and then the integral of x cubed is going to be x4 over 4. So I'm left here x cubed times x4, and that's going to be proportional to h, which is the distance. So that's good. At least I'm consistent here. I find xcm. The position of center of mass of a cone is 3/4 of h. If I start from the tip of the cone, or I could also say it's just 1/4 of h if I start at the base. Yeah, if I look at the picture here, it's going to be 3/4 of this length here, or 1/4 of the length if I start from the base. So that's good to know, easy to remember. Interestingly, it's independent of A, the radius or the angle of the cone doesn't play any role, only the height. So if I have different cones but they all have the same height, the center of mass is going to be 1/4 away from the base. How about that? Any questions? Yeah?
So if we know the height from data given to us, we can literally just plug in that equation here.
Probably, unless you ask to prove that it's there. Otherwise, yeah, you could probably just go ahead and say it's h/4 or 3/4 of h. In fact, we're going to use that in the next exercise. Yeah, it depends of the exercise that you asked to. So now we're going to do more and more complicated shapes. So far we've seen rods, discs, triangles, rectangles, hemispherical shells, and cones. What if we have a composites of those shapes? What if I have a pencil like this? So that's like a rod and then a cone at the end. Or one like that. That's a rod and then a hemisphere at the end. Or one like that. We have all three. I could still use all this information I've gleaned before and put it together. Here, I just give you the theorem. If I have two pieces making, well, they should be together, I guess, making a composite shape, and I know the center of mass of one shape, center of mass of the other shape, then I can find center of mass of the whole body. And it kind of goes without saying. There's the proof underneath, but I don't think we need to go through it. That the position of the center of mass then is going to be the weighted average of the position of the centers of mass of each part. And similarly, if there was 3 parts and 4 parts, yeah, you just go back to the definition and you'll see that it's just a matter of writing it. There's no calculation really, just definitions. Right, so here's the proof. Makes sense. You're just adding all the masses of all the particles, and instead of doing the entire sum, you just divide it into 2 parts, and each part will give you the center of mass of each part. So, makes sense. So let's try to do that for this example. So that was in an exam a couple of years ago, exactly the one I was telling you about, the pencil that's been used a lot. Just down to the final part. What's it made of? First there's a cylinder. So for the cylinder, we know by symmetry here's the cylinder, where the center of mass is, right? It's going to be exactly, okay, I shouldn't have done that, exactly in the middle. It's going to be just here. I'll show you a different color. Center of mass of the cylinder. We know where the center of mass, so it's going to be, if that's the origin, it's going to be at distance, and x is going this way, it's going to be at distance plus h from the origin. Since okay, makes sense. What about the cone? We know that the center of mass of the cone is going to be 1/4 away from the base. I'm counting from the base because that's where the origin is. It's going to be 1/4. So it's going to be just a. It's going to be minus h. That's going to be the position of the center of mass. here. Mass of the cone, which is why this is what's written here, h and minus h. Okay, so we have the center of mass of the two parts of the rigid body, so we could find center of mass of the whole body. Yes?
Why is it minus h?
So it's the distance is h, but I'm just doing I'm on an axis, right? So in this direction it's plus, then that has to be minus. Or you could have taken O to be here, then you would have had the distance of the position of the first one is 3h, and the position of the second one is going to be 5h. Wherever, depends where you pick the origin. Let's do it now. Let's do it this time. 5, 7, 3, 22, 23, 4, 5, 6, 7, 9, 10, 11. Duck, duck. Poor guy. So we know the position of the two centers of mass. We're going to find the position of the entire thing. Not too bad. Yeah, we just need R1, R2, and then we need M1 and 2 and M, the total mass. We don't know it, but we could figure it out from the mass density, right? So we need the volume of each part multiplied by the mass density, you get the mass. So it's nice to have a table like this because we can fill it up. The cylinder, what's the volume of a cylinder? Oh, it's there, it's the first. Well, you get it, right? It's the surface of the cylinder times its height. So in this case, it's going to be, A is the radius, so it's going to be pi a squared times the height, which is 2h. Volume of the cone, that's in the book as well. 1/3 pi r squared. Here the radius is a squared times the height, which in this case is 4h. Volume of the pencil will be the sum of those two volumes. I have to add 2 and 4/3. 2 plus 4/3. So that's going to be 10/3 pi a squared h. And now to find the position of center of mass, I just use my formula from before. M1 times A, 1 over M times M1 times H plus M2 times minus H. That's all I write. So to find M, M1 and M2, I need the mass density. So the mass density, remember, is the same everywhere. It's uniform. So total mass, that's M. Total volume, that's 10/3 pi a squared h. But it's the same for the first part and for the second part of the pencil. So I have mass of the pencil M equals rho times 10/3 of pi a squared h. Yeah, I get M have to multiply by 10 pi a squared by h and divide by 2. Yeah. Mass of the cylinder M1 It's going to be rho times V1. And V1, I have it on top there. Pi A squared A or 2H. Okay. I'll write it here. 2 pi A squared H. Mass of the cone. Okay, from here, M2 is rho V2. And V2 is 1/3 A squared. Wow, that's 4H. Brought the 4 to the front. The 4 to the 4. 4. Okay, so now I can just compute the center of mass of the pencil. It's going to be 1/m times m1 position of the center of mass of the cylinder plus m2 times position of mass of the cone, which is minus h. And then I just fit that in and compute the position. That's all. So now it's just boring maths. 1/m. So rho 10/3 pi A squared H times n1 rho 2 pi A squared H times H plus m2 rho 4/3 pi A squared H times minus H. Okay, that's it. Some tidying up. I see that the rho is on top and bottom. The pi, the A squared, and the H as well. That's here, and that's here. So I'm left with 1/10, that's going to be 3/10 times, at the top I have 2h minus 4/3 of h. So what's that? 6h minus 4h over 3 2h over 3. So that's h over 5. That's what it is. What do you think? Okay.
So for the pencil, like the volume, you said it was just H, right?
For the cone.
For like the pencil as a whole.
So the pencil have a hole. We just computed it here.
Yeah.
H over 5. So it's going to be inside the cylinder rather than inside the cone. Yeah. We find the positive number, so it's going to be somewhere here.
I was thinking like 6H.
Should the well, you can do the exercise like the guys told us. Put your 2 fingers. And you find that's at H over 5. You will expect it to be on this side? More? You can't tell until you do the calculation. It's all due to those dimensions, right? Maybe if it was much longer and this one was shorter, probably going to shift towards the center. Yeah, you could actually, oh, that's a good exercise. Find for which height of the cone the center of mass can be at O, for instance. Crazy. Yeah, you wouldn't expect that. Any other question? No? We take a short break. What about this problem here? a ball. So you get the idea? That's hollow, right? There's an outer shape, which is a hemisphere of radius A, and then there's an inner shape, which is another hemisphere, radius B. And the matter is only in between those two boundaries. That's why it's called a ball. Where is the center of mass of this? So it's not a composite. Well, we don't know how to do it. Can we use what we did just before, a composite? Is it a composite? It's not. But we can imagine a composite that's made of this and a hemisphere of radius B. And if you put them together, then you have a hemisphere of radius A. Yeah. That's why I wrote here in this sentence, imagine filling in the ball with a solid hemisphere of the same density with radius B to form a solid hemisphere of radius A. Yeah. Then I will have a composite. Even though it looks uniform, I could think of it as two parts. One part is the small hemisphere and the other part is the ball. So instead of adding, I'm subtracting. Blows your mind. Let's do that. Oh, I forgot to say something. Yeah, here I should have made it clearer, right? That's middle of the cylinder. And here, that's 1/4 height from the base. So those tables are very handy. Let's do it here now. Solid hemisphere of radius B. Where is the center of mass? We saw that in the previous lecture. It's at 3/8 of the radius, which is B. And similarly for the solid hemisphere of radius A, we are 3/8 of A. And then if I put those two together, I don't know the center of mass of the ball, that's what I'm looking for, but if I put them together, I get the third line. So what about volumes? So hemisphere radius B, I know that the volume of a sphere is 4/3 pi r squared, so here's going to be 2/3 pi B, cube, not squared. Similarly for the other one, 2 pi A cubed. And so the volume of the ball is going to be one minus the other. So that was easy. A cubed minus B cubed. So, just like in the previous example, I have a table where with only one unknown. I can do the calculations quite easily now. So, the center of mass of each hemisphere, okay, I should say. Its center of mass is such that, and I'm going to use this composite formula, right? The solid hemisphere of radius A is composed of two bodies, the solid hemisphere of radius B and the ball. All right, so I'm going to write that the position of the center of mass, I have it above there, the last line of the table of the hemisphere radius A is 1/m, so I just write the formula, and I know m is going to be rho v. V is 2/3 pi a cube, I know M1 is going to be rho V1. What did I write? Sorry. It's not V1. It's X1 M2 X2. Sorry, it's the positions. So M1 is going to be rho V1, and V1 is 2/3 pi B cubed. Position of X1, I have it on top here, is 3/8 of B. And then M2 is going to be rho V2, which is 2/3 of pi A cubed minus P cubed. And the position, I don't know it, is what I'm looking for, XCM. So now I just have one equation with one unknown, and I can solve it. So I have rho on top, I have rho 2/3 of pi on top and bottom. I can delete that. That's gone. So what do I have? I have 3/8 of A equals, so that's from 1/A cubed times the parentheses. So I'm going to bring the A cubed to the left. It's going to be 3/8 of A to the power 4 equals, and on the left I have 3/8 of B to the power 4 plus A cubed minus P cubed times X CM. Oh, I don't need that bracket. Yeah. So now I can find XCM. XCM is going to be 3/8 A4. Who's coughing? You've been to China, Italy, US, Brazil, France, the UK. Any? No? Okay. I have a visitor from Italy at the moment, so might be patient 0. Anybody watch Infection? David Soderbergh, 2011. No, Contagion. That's what it's called. Everybody seen Contagion? Such a great movie. Patient 0 is Gwyneth Paltrow. She dies promptly. So XCM, that's it, we found it. It's going to be 3/8 A4 minus B4. So you can leave it like that. You've answered the question. You could check if the answer is consistent with previous results. Yeah, we can do that. We could do nice checks. We could, for instance, say check 1. What happens when B goes to 0? So B, remember, is the radius of the hole in the ball. So if it goes to 0, then you're gonna have a full hemisphere. So what do you recover then? XCM tends to, that goes to 0, 3/8 of A4 over A3, you get 3/8 of A. So that's good. 3/8 of A, consistent with last lecture. Oh, should add insert page. What about checking when a goes to 0? No, sorry, when a goes to 0, then there's nothing left. What happens if b goes to a? If the hole grows to be the same dimension as the outer limit, so then we're going to be left with just a shell, hemispherical shell. So we should recover the result from yesterday as well, which was that the center of mass was exactly at the halfway at a over 2. So let's do b goes to a. That's no good because we're going to have 0 over 0. So we need to think about that better. But I can see that I could have simplified that expression because both top and bottom can be factorized by a minus b. Yeah, at the top I have a product of 2 squares. So we have the difference of 2 squares. So I can factorize. And that's again the difference of 2 squares, so I can factorize it even further. I can do a plus b, a minus b. And at the bottom, I can also factorize by a minus b. And I have to do long divisions. I don't know how you do that in your head. Everybody has a different way. So I want a cubed, so I have to start with a squared. That's going to give me a cubed minus ba squared. So I want to get rid of the minus ba squared. So I need to put a plus ba squared plus ab. That's good. And then I need the minus b cubed. So I need b squared. Yeah, maybe I'm wrong. Whichever way you do it. So that removes the singularity. Top and bottom can be simplified by a minus b, and I can take the limit when a or b tends to a. At the top, it's going to tend to 2a squared times 2a. That's going to be 4a cubed. Then at the bottom, it's going to be 1, 2, 3a squared. So XCM tends to 3/8 of 4a cubed, 3a squared. And that's the 3 simplifies, that's just a over 2. Yes, as expected. From the previous lecture. Nice. All these maths coming together. Yeah, algebra, integration, differentiation, mechanics. I'll see you tomorrow then. Take care. Thanks very much.